what will elasticity of substitution do? It will take into consideration both the things simultaneously. So my elasticity of substitution, which is sigma, is given by how does this ratio changes upon how does MRTS changes. So this is log d of log of k by L upon d of log of MRTS. Okay. So if I have to solve it, let's solve this a little bit. So this is d of ln k minus ln L, because I'm taking log. So log of ratio, log of m by n is log of m minus log of n upon d of ln Mpl minus ln Mpk. Am I okay with this? Good. So this is log differentiation is 1 by k dk minus 1 by L dl upon 1 by Mpl d of Mpl minus 1 by Mpk d of Mpk. So you can solve this for different functions. So let's solve it first of all for the Cobb-Douglas function. So supposedly my function is this. So above would remain the same. So I will have 1 by k dk minus 1 by L dl upon what will be MPL. MPL is when you differentiate the function with respect to L. So differentiate this with respect to L. What do you get? So you will get half into k to the power half L to the power minus half. So this is half k to the power half upon L to the power half. And when I reverse this thing, I will get half into L to the power half upon k to the power half. And I have to differentiate the MPL function also now. So I have to differentiate this. So differentiate this function. So how do I do that now? So MPL is how does output changes when labor changes, and I have to differentiate this function. So this will be how does output changes when labor changes again plus this. Right? So I will write it as d of half L to the power half upon k to the power half minus d of half k to the power half upon L to the power half. Alright, and now I will differentiate this. So let's do this. So what will I do is the following. Now understand here, I can bring half out. So I'll say half into L to the power minus half dl. I'm differentiating it with respect to L. So differentiation. So I'll use quotient rule here. So differentiation of the first function into second as it is minus differentiation of the second function. So this is half k to the power minus half dk into L to the power half. So upon second whole square, so which is k to the power half whole square. So what do I get? I get 1 by 4 k by L to the power half d L minus L by k to the power half dk upon k. Similarly, when you solve for this thing, it's exactly the opposite of this. So I will get minus 1 by 4 upon L. Okay, just the opposite of this. And then what are you, so this is my denominator, and then I'm going to divide this by that. So when you do that, so when you solve that, so first of all you will get this as your second term, this, and then you can solve this. Okay, and after solving and dividing you will get 1, and this will hold true for any well-defined Cobb-Douglas function, that the answer would be 1, and they are therefore also known as constant elasticity of substitution function. Okay, so the next function that we want to go about is min function and substitute function. So suppose my function is a k plus b l. Now my MRTS would be a by b. Sorry, suppose I'll just take the opposite so that you don't get confused. So supposedly my function is al plus bk, then my MRTS would be a by b. So d of ln k by l upon d of ln a by b. So this is a constant, so differentiation of constant is 0. So this is anything by 0, whatever this will be. So the answer would be anything by 0 would be infinite. Okay, now let's take the min function. So for min function, my function is min of ak by bl. So when I equate, so I will always equate whatever comes inside the bracket. So I know that ak is equal to big L, or I know that k by l is b by a. So now my elasticity of substitution is d of ln k by l upon d of ln MRTS, which is d of, so this is d of b by a, ln b by a upon d of ln MRTS, but this is a constant, so this is 0 by anything, so 0 by anything is 0. So for min functions the elasticity of substitution is 0, and for the ln, for the substitute functions the elasticity of substitution is infinite. Thank you.